So when we're checking the overall stability of an object, we're going to have to check two things. We're going to have to check sliding and we're going to have to check overturning. Now, we've already looked at overturning, and now we're just going to have a look at sliding. And in this case, we're looking at a filing cabinet, so maybe someone's pushing it. So maybe you're checking that, a small child can't push this thing over and hurt themselves or something like that. So there might be some rules about the minimum force you would need to push these things over at different levels, something like that. Excuse me. And so what we'd have to do here is we're going to have to check. So what we've got, let me just see what we've got first. So you've got a filing cabinet, it weighs 2 kilonewtons, so it's about 200 kilos, something like that. And so it's getting pushed by a load P at a height Y above the base. And so we're going to try and find whether it's stable for some different loads at different heights applied at different heights above the ground, and see if it's stable or not. So we'll start with P is 500 newtons, Y is 0.5 meters. So let's just do a free body diagram first. And so we'll get rid of the floor. We'll get rid of these dimensions. We've got them above anyway if we want to check anything. And I think each of these is 0.25. Each square is 0.25 meters. 0.25, 0.5, 0.75, 1.25. So in the first one, it's getting applied 0.5 above the ground. So we'll take that and put it at 0.5. And it is 500 newtons. What else have we got acting on this? We've got the weight, and we're applying a horizontal load, and so we don't really need to worry. We'll assume that filing cabinet's evenly loaded, and so we're going to have, I might have to do this in a different color, or I might just do a free body diagram that doesn't have all the details, just to make things a bit easier to see. And so we're going to have the weight of the filing cabinet acting down the way. And then this time we will probably try and, I think, just to illustrate how to calculate where the reaction force would be, we'll just assume, so this time we'll actually calculate where that would be. So we're going to have the weight down. The reaction force must balance that, so it's going to have the same magnitude. So it's going to make a couple at normal force, the reaction force from the ground. A bit too long now. I'll just leave it at that. I'm not drawing it accurately. And then we're also going to have, in fact, nothing's to scale. I'm just looking at my 500 newtons. The actual weight is 2 kilonewtons. Let me just shorten that a little bit. Just try and tidy everything up so it looks sensible. And then we're going to have a friction force, like so. Oh, excuse me. And we'll call that F just now. So we don't know if it's at the limit or not. If it was at the limit, we'd call it Fs, but we'll just call it F for friction. We'll call this one W, and we'll call this reaction force N. And we'll calculate where that is this time, because it can be useful to do it that way, but we don't really have to do it that way. Let's just put it on for now. So that's going to be X. And what else do we know? We know that this is 0.5 meters here. Now, let's do first things first. So let's check for sliding. And so what we'll do is we'll just check the horizontal forces. They should be the same magnitude. And so that's using sum of the x components must be equal to 0. So the sum of the x components must be equal to 0. So that means that 500 newtons, so we've got that 500 newtons, and then the only other x component is the frictional force. So minus. We should probably put on our axes just to show what we're assuming. So I'm just going to use the standard directions for the X and Y axes. And so we're going to do 500 minus F equals 0, therefore F is equal to 500 newtons. Would be the force. And now we can also calculate Fs, so the static friction. So that was the maximum friction you could get for this normal force of W. We're going to have to do is calculate W first though. So W is going to be, W is going to be mass times, no, it gave us it in kilonewtons, didn't it? And so 2 kilonewtons what the cabinet may weigh, so we don't have to worry about that. W is just 2 kilonewtons. So therefore Fs, well, which is equal to the normal force. And then we're going to get Fs is equal to coefficient of friction times the normal force, which is equal to, does it give us a coefficient of friction? It hasn't. I'll fix that. So we'll assume the coefficient of friction is equal to 0.4. It should have been given in the question. So Fs is 0.4 times the normal force is 2 kilonewtons, which is equal to 800 newtons. So it's 0.8 kilonewtons, 800 newtons. So therefore we know that the friction force we need is less than the static friction, the maximum we can get. So remember the graph. So they're equal to each other up to a certain point and then it drops away. And this is your Fs here. It's the maximum friction you can get. So F is S less than Fs, therefore will not slide. And then there's two ways we can check for overturning. So check overturning. And to be honest, the way I would always do it is this first way, which is what I showed you last time. A week or so ago, maybe a little bit longer, a couple of weeks ago, we looked at checking for overturning when we looked at moments and centroids and such like. And so let me just see if I've got a little sketch here. So if this cabinet was going to overturn, it would overturn about this point here. Let me do it in green. So it would overturn about that point there. So what we do is we choose that point A, and then we check the moments. So with the restoring moments and the overturning moments about A. And so the overturning moment is going to come from the 500. So the friction goes through A, it's at the base, so it's got no moment. So we're going to have 500 times its lever arm. It's going to be the overturning moment. So this one here times this lever arm, which should have been 0.5. And then the restoring moment, what's going to turn it back the way to make it sit down, is the weight times this lever arm here. And so we'd have that lever arm. I think the whole thing was 0.5 wide, wasn't it? So that's 0.25. So overturning moment. And usually when we talk about overturning moment, we just write down the magnitude. We don't really worry about direction. The fact that you're calling it the overturning moment tells you the direction. So overturning moment is equal to 500 times 0.5, which is equal to 250 Newton meters. Restoring moment is equal to, so the weight is equal to 2 kilonewtons, so 2000 newtons, times 0.25 is the lever arm for that restoring moment, which is going to be 500 Newton meters. So I should probably, might be handier to give those some letters. So let's do that. MOT, MR. So the restoring moment, what's making this thing sit back down, is greater than the overturning moment, what's trying to push it over. So that means will not overturn. So therefore, so it won't slide, it won't overturn, so therefore it's going to be stable. Now let's call that method 1. So that's one way you can check it. That's the way I would usually use. But the other way you can do it is you can check where this reaction force N would be. So you can check where that would be. And then you can make sure it lies within the base of the cabinet. And so you can imagine as I try and push this further and further, this N is going to move further and further until it's just sitting at the corner. If you do a calc and you find that N's beyond that point, then it's going to fall over because N can't be out here. So it must have already fallen over. And so method 2. So what we can say is the sum of the moments about A must be equal to 0. So the sum of the moments about A must be equal to 0. Then we'll think about all those moments. So what we're going to have, this value here times its lever arm. And that's going to be a negative moment. So that's negative 500 times 0.5. And that's actually a couple. So it's the same 500 times 0.5. It's a couple, these two things here. And then we're going to have, we could do it in terms of, we could do W and its lever arm to here, and then we could do N and its lever arm to here. But actually these are a couple as well. So that is the same magnitude as that. And so we can calculate the moment of that just by doing the, so this reaction is the same as the weight. So it's just weight times X, and it's going in the positive direction. So it's plus Wx must be equal to 0. We know the weight, it's 2 kilonewtons, so 2000 times X must be equal to 500 times 0.5 is 250. So therefore X is equal to 250 divided by 2000, which is equal to, let me just figure that out, just a second. I should be able to do that in my head actually. 1/8, so 2000. Yeah, it is an 8th, 0.125. So this point N. So what we've done here is we've got two couples, so we can just, for a moment from a couple, you could do it about A, but you can also just say, look, it's a couple, so it could be anywhere, it doesn't matter, but you just do the force times the distance between the two equal forces. And similarly, this is also a couple, so we could do each of these about A, but you'll find it's just the same as doing this force times the lever arm between the two forces, and this is called N, this is called W, but they're the same. For equilibrium, they must have the same value, therefore it's a couple. And so we just equated those. Then we found out that this distance X is 0.125. The total width is 0.5. So this is 0.25. So this X is less than 0.25. Therefore, will not overturn, because it's that reaction force is sitting within the width of the base. Okay, and so for this scenario, so overall we're saying now, so for this scenario where we've got a force of 500 newtons at a height of 0.5 meters, the cabinet is stable. So for P equals 500 newtons and Y is equal to 0.5 meters, cabinet is stable. Now, let's have a look at the next one now. So we've got 1 kilonewton at 0.5 meters. Do I want to start again? I'll just use that one, it's not so bad. In fact, it's 0.5 meters, so this is B now. So let's have a think about this one. So we've got 500 newtons. So this time we've got, what did we have? 1,000 newtons this time. 1 kilonewton, so it's 1,000 newtons. I'll just stick with newtons, I think, because we're going to get some smaller values. 1,000 newtons. Otherwise, it's all pretty much the same, really. So 0.5 meters, we've got X. So we know that that would mean for no sliding, or let's say this actually. So what we can say is to look at sliding, we basically look at the X components. So sum of Fx must be, or let's say for static equilibrium. For static equilibrium, we must have the sum of the X components is equal to 0. So that would mean, so we've got 1,000 newtons here and the frictional force resisting it. That would mean 1,000 is in the positive direction minus F equals 0. So F would have to be 1,000 newtons. But if the maximum frictional force is equal to the coefficient of friction times the normal force, which is equal to, we're saying it's 0.4 times our normal force was 200, was it? 2 kilonewtons. So 2,000, which is 800 newtons. So F would need to be greater than Fs, therefore will slide. And you'd probably just stop there because it's going to be sliding. It might also be overturning, but we know that it's unstable. But let's have a look. What did the question ask us for? Determine where the cavity was so blah blah. If the cavity's unstable, state the mode of instability, sliding or overturning. So probably what we should do is we should check this, which is going to happen first. Will it slide first or will it overturn first? Now the way we can do that, so this here is really to do with sliding. And probably should have stated that. So let's just move this stuff down and we'll just say what we're doing here. So this is check sliding. And I would usually start with sliding first. It's the easiest one because you're just checking the X components. You don't have to worry about moments or anything like that. So they would check the sliding first. Now, but we could figure out what will happen first. Will it overturn or slide first? So check overturning. And so what we can do is we can check what would happen at the point at which it's going to slide. Okay, so the maximum force we can get here, the maximum frictional force is just your static coefficient of friction times the normal force tells you the maximum frictional force that you can generate, and we know it's 800 newtons. So we will get up to 800 newtons and then this thing will start to slide. Let me just grab this again, we'll just copy that down. And so if we were imagining increasing that load slowly, then we would get to 800 newtons here. So let's just label this diagram. So free body diagram at impending sliding, let's say. Yeah. To go back to primary school, impending sliding. Learn how to write. I do apologise for all my coughing and spluttering during these recent videos, just this cold. Free body diagram at impending sliding. And so what we know at impending sliding is that this here is Fs, and it's going to be 800 newtons. We've just figured that out here. And so therefore, if we were imagining increasing the force, the point at which it'll start to slide would be when this was 800 newtons. And so at point of impending sliding, we know that, we know that P would be equal to 800 newtons. Then we can check, so the overturning moment would be equal to 800 times 0.5, which is 400 Newton meters. And the restoring moment, again, we're not worrying about plus or minus because we're talking about overturning and restoring. These kind of have the direction wrapped up in them. And so we're looking for our point of rotation would be A. We talked about that up here. What have I done with it? Yep, so it would rotate like that. So that's going to be a point of rotation at A. The restoring moment is just from the weight, is the only thing that would bring this thing back down again. And so it's going to be 2,000, excuse me, 2,000 times 0.25, which we've already figured out would be 500. Is that the same as we got before? Just going back up and check. Where did we do it here? Yep, so 500 Newton meters. And so what can we see there? So at that point of impending sliding, we will have the overturning moment is less than the restoring moment, therefore not overturning. So therefore sliding would be critical. So it's going to slide before it overturns. So what do we know? And it's going to start sliding when that force B is 800 newtons. And a question might ask you that. It might ask you, look at what point, what's the maximum load you can apply while this is in static, to keep this in static equilibrium, or while retaining static equilibrium, and you do something similar to this. So you'd calculate what force would make it slide, and then you can also calculate what force would make it overturn, and just see what answer you get. So lots of different ways you can do this. It doesn't have to be this way. And so what would we say? So the question was asking us, you need to go back and figure out what the question was asking us again. Terminally pilot stable. If it's unstable, state the mode of instability. And so we'd say for P equals 1,000 newtons at y equals 0.5. Cabinet is unstable, is not stable. We can say sliding is critical. So one more part to do, which is just we're applying a 500 Newton load higher up at 1.25 meters this time. And then we'll have a look at what the critical mode of failure is this time. And we'll figure out whether it's stable or not. So I've already drawn the free body diagram for that. I'm not going to put in this yet, so we'll just call that F for now. And so we'll go through the same process. What you'd expect is it's more likely, because this is higher up, you get a bigger lever arm, so the overturning moment is now going to be higher. And so you'd expect that the overturning moment will become critical. But we know this 500 newtons. We've previously calculated that Fs is 800 newtons. And so we can take some shortcuts here. For sliding, let's say, so from the free body diagram, we know that sum of the x components must be equal to 0. Therefore, we're applying 500 newtons in the positive direction minus F is equal to 0. So F must be equal to 500, which is less than Fs. See above, we've already calculated it. So that means sliding is not critical. So let's check the overturning now. So for overturning, so we again, it's the same point of rotation. You're always thinking about this. A is your point of rotation. Sorry, there we go. And so we're going to have sum of the moments about A. Oops. For static equilibrium, this is the sum of the moments about A must be equal to 0. Oh, no, we will not do that. We'll just do what we've been doing so far. So MOT, the overturning moment, is this one. So it's trying to overturn this object. So it's going to be 500 times 1.25, which is equal to 625 maybe, Newton meters. Double check that. It's definitely 500, wasn't it? 500 times 1.25, 625 Newton meters. The restoring moment is equal to 2000 times 0.25, which equals 500 Newton meters. So we have MOT, the overturning moment, is greater than the restoring moment. And I haven't defined these here because I've already defined them earlier. Where did I define them? Up here I said what MOT and MR were. But if you were in an exam, it might be better to just write out what these are. So the overturning moment, comma, MOT, the restoring moment, comma, MR, just so the marker, the person reading your calcs knows what you're talking about. Therefore, unstable. And so we can see that the overturning moment's critical for this arrangement because it wasn't, even at that load, it wasn't going to slide, so it's going to overturn first. So for P equals 500 newtons at Y equals 1.25 meters, the cabinet is unstable. And overturning is critical. Excuse me. Okay, and so that's us done. So basically for these types of problems, if it looks like overturning might be an issue, then you should be checking both. Check sliding and overturning. Just remember when I always do sliding first because it's easier. So check the sliding, see if it slips. If it doesn't slip, then check overturning. And what you might want to do is just to check whether, so say it will slide, but it's asked you for which mode of failure is critical. Well, what you do is you put in that frictional force, the maximum frictional force you can get, and check whether it would overturn for that maximum frictional force. And if it would overturn for that, then overturning is going to be critical. Hopefully that makes sense. Have a think through it. If it doesn't, try and figure it out for yourself or have a look online. And you can remember that there is always another way to check for overturning, and that's to make sure that this normal force lies within the base of the object. I tend not to use that. I tend to use restoring moments and overturning moments, but that's another way to do it. Is just look at whether that reaction force, the position of that reaction force to counterbalance the moment from the applied force, positions it so that it sits within the base of the object you're looking at. Done.